Hello guys, Mapetla here again. Sorry, but this time our video just got on away because of power cut off. So today I'm to continue from there. So I want to believe we're dealing with ordering real numbers. The principle of trichotomy. Yeah, properties of real numbers. We ordered them, and we were on properties of real numbers. Okay. So it's properties of real numbers. Let me use a red color and a red. Properties. Properties of real numbers. Properties of real numbers. That first is dealt with ordering, which I explained the order in real numbers. And then second, the principle of trichotomy. I think it's written this way, is it? Yeah. Trichotomy. Okay. Okay, got it. So this principle of trichotomy, I explained to it that is given two or more real numbers, two real numbers, A and B. So this is the red, A and B as elements of R, which means they are part of R. So being given two real numbers, we have three possibilities. One possibility is that A is smaller than B. Second one, okay, should I write whatever? Put it in brackets. Then the second one is A is greater than B. And of course, the third one, it's A is equals to B. There are these possibilities. So if we have two real numbers, it's either those real numbers are related in such a way that they are equal, or when one of them is greater than the other. I'm really sorry for using siblings for A and B. I'm sorry for that. And that is it. So these things we dealt with them in primary school, you know. Like for example, A, can say 5-15. We have to put a sign there, and then obviously that sign there, 5 is smaller than 15, so it's going to be that sign greater than, right? So doing that all the time. Maybe half dash 0.5. We know they're equal, and these are the things that we'll be dealing with, you know. So it's really nothing hard. Today I'm dividing because I didn't write much. No, let's forget about the divisions. Let me add another page. Adding another page. The next one is intervals in real numbers. Intervals in real numbers. Intervals in the real number line or in R. Intervals in R. So if we have real number line, we get that. Remember that the real number line can be represented as this X being an element of real numbers, or it can be represented as numbers from negative infinity. Oh, there is no equal sign for infinity. Negative infinity, X, and infinity. So X is bigger than negative infinity, and is smaller than positive infinity. So this is the number line. I can say this is the number line. You can say that is the number line. And having the number line is that we have a lot of communications, really. We have a lot of communications with respect to that. And we can have, okay, can have a table. I've seen in our book, they use a table. The table goes like the table. Let's see. Now, let me look at it first. You know, as for intervals in real numbers, we have bounded intervals. So we have bounded intervals. Bounded intervals in R. So bounded intervals are those that have limits which are defined. That is, it bounds the exclude infinity and negative infinity. So I think we know them. So now I'm going to demonstrate or write them down as a in a table form. So we have notation. Let me say 1 maybe. In figure 1, notation. Notation, the other Roman figure. I think it's going down straight a little bit. And another notation can be the interval type either open or closed, interval type. And then the other one is the representation in inequality form. Inequality type or inequality form, and representation in real number line. Representation in real number line. In R line, yes. And then we can have a straight line dividing or stuff like that. Anyway, it's going a bit low, so sorry, it was not supposed to be 1. 1 is supposed to be here. So therefore, number 1 we have something like that. Square bracket A comma square bracket B. Interval type, this is perfect closed. Okay, it's a closed interval. Let's remove perfect. Should remove perfect from that. So it's a closed interval. So when we represent it in equality form, it is going to be in the form of A smaller than or equals to X, which is smaller than or equals to B. Representation in the real number line, that is, if we have the real number line like this, I'm failing to draw straight lines, you know. Okay, whatever. Having that and having negative infinity there and positive infinity, having A here and B here. When you represent it in the real number line, since it is a closed interval, we are going to show by square brackets. So that is, we're going to do this, exactly passing there, and then do that, and then join with a straight line. Right. Make sure a straight line can be seen, right? Just draw one. That is a representation in the real number line. And then Roman figure number 2, we may either have A open and B closed, or open open. Okay, let me have open open. A comma B, all not having a closed interval, so that is an open interval. An open interval, so representative, it's going to be A smaller than X, which is smaller than B. And I'm really sorry about my spacing here. Things are not going well with me and my things. Straight line, like that. Sorry. So it's going to be A smaller than X and X smaller than B strictly. Representation in the real number line, we're going to have a straight line as our real number. And then if A it's here and B it's there, we're going to have a curved bracket there and a curved bracket here, and we are going to have a line joining them. It represents that is all numbers in between these bounds of ours, they are open bounds. Our bounds here, excluding them, so whatever number that is in between. Here, it's all numbers in between A and B, including A and B themselves. So that is a closed interval. And then we have 2 more types. That is A square bracket, comma, B open bracket. This one is not conclusive because the other one is, oh, sorry, I didn't draw well, but sorry about that. This is supposed to be a curved. So this is not conclusive because we have the other side closed and the other one open. So we can't conclude either closed or open, and we can't say open closed. So we say no conclusion about interval type. So then representation as an inequality form, you're going to have A is greater than, no, A is smaller than or equals to X, which is smaller than B strictly. Representation there is going to be an easy one. So if we have A here and B here, we are going to have a square bracketed A, a square bracketed A, and a curved bracketed B. So then we join them with a line to show that all numbers in between are included in the interval. So then we are going to have our fourth type. That's what I'm learning to use this thing of internet and technology. I'm adding a new page, by the way. So yes. So in this new page, allow me to move this whatchamacallit here down to where I will not have to stress about using it. Yes, they. Okay, the last one, it's Roman figure what? 4. Sit written as IV. Okay, interval type, it's going to be A open. Oh, buddy, did I write it like that? Yes. Okay, first of all, it was a notation. And then B closed. Interval type, not conclusive. And denotion in terms of inequality, it's going to be A, it's strictly smaller than X, which is smaller than or equals to B. And denotion on the real number line, we're going to have a real number line like that. And having A is open, and B is closed. B is there, and A is there. We're going to have something like that. And then have a number, have a line joining them. Please make sure that your line doesn't pass like mine here. I made an error, but let me wrap that, make it perfect. You know, yes. So make sure you have a line coming from there to there with a passing, and it's a curve, it's a square. That means it's all numbers in between these two bounds, but A is not included, but B is included. So it's part of those numbers that we're talking of. So that is really the inequality types. Then what they are bounded, or they have limits which are known, which are real numbers. So now unbounded ones, unbounded intervals, Bounded intervals are those that include infinity. Infinity is in there, either plus or minus. Infinity is there. So it's really, this really we know, This really we know. We can have all open and some are not conclusive and whatever. So at infinity, we shall never have a closed interval. So we have notation, interval type, inequality representation, inequality denotion, and representation in the real number line. Representation in the real number line. Then supposed to have that, and that. So they are, how many are they? We have 5, I think. It's not going well. Okay. Okay. All right, there we are. So the first one, we can have close bracket A, comma, positive infinity. So this interval type is not conclusive because A is inclusive and C and infinity is not inclusive, so no conclusion. And then representation in the real number line, no, representation as an inequality form, we are going to have that A is A is smaller than X. A is smaller than or equals to X. We can put, okay, if at all A is smaller than X, it means that it can be bigger than, if X is smaller than A, it means that it can reach out to infinity. Or we can just include it and say smaller than infinity, which is so obvious. So oftentimes we don't really put this infinity thing and just leave it as, when we just leave it as A smaller than X. A is always smaller than X. So representation in the real number line, we're going to have, if we have our real number line V, and we have our letter A here, we're going to have a square bracket. A square bracket. I know it's not so visible here. We're going to have a square bracket at A. That is our A. And then we'll be having it go into infinity, because infinity is the last positive number there. But in fact, infinity, according to me, is not really a number, but it's just an approximation of a very, very big number. So that is really how we are going to represent it. I guess it's easy. And then we can have something like open A, comma, infinity. Remember, at infinity, we cannot close our, bounds, because infinity is simply a very, very big number that is not known. Henceforth, we can't really say we know the great number infinity, but we just approximate it to be a very, very large number, which we don't know. So yeah, no, you cannot simply say it is an exact number, because it's a very, very big number. So that's why it is always open. So that is it. And let me see how I'm gonna go about these. Okay, the notation for this next one is A open, comma, infinity. So this is entirely an open interval, because this side is open and this side is open. Henceforth is an open interval. So therefore the interval type is an open interval. And representation, it's A, it's smaller than X with no equal sign. A is strictly smaller than X. They are not equal because we don't have a square bracket there. Henceforth, it's like that. And then representing it in the real number line, we're gonna have something like this. Here's our real number line. If we have A here, we are going to have a curved bracket, then a straight line with an arrow there. That is a representation that it's all numbers which are strictly greater than A, with A exclusive. And the next one, it's going to be, you can put it on the right hand side, something like negative infinity to B inclusive. So this one is positive, and what am I saying? It's an open and closed, hence no conclusion. So the interval type is inconclusive. So then the interval type, it's going to be that X, it's smaller than B or equals to B, because it's a square bracket there. So therefore, we should put an equal sign. So representing it on the real number line, okay, this one had an arrow. It is going to be, I'm not able to draw a straight line. Okay, if we have B here, we should have a square bracket and a straight line with an arrow. It shows that it's all numbers less than B, strictly less than B, including B itself, because we have a straight line there. No, we have an equal sign there. So therefore, it's all numbers smaller than B, including B. So the next one is going to look like this one, but having negative infinity to be all open. So this one is strictly an open interval. So representation, it's going to be X, it's smaller than B, strictly with no equal sign. Therefore, if we have a real number line like that, and we have B here, what should I do? Let me see. All right. If we have B there, you're going to have a capped bracket, and then I'm drawing it with a capped bracket like, yo, bruh, what happened to my writing skills? Okay, a capped bracket there, and then a straight line and an arrow. Remember there we have negative infinity, for all of them, negative infinity, positive infinity, positive infinity, positive infinity. So therefore it will just be like that. And then the last one is going to be strictly open interval, negative infinity to infinity. This one is entirely an open interval representation. It's going to be just R. X can be anything really. So there is no need for us to put bounds, or we can simply maybe do this. Remember, infinity doesn't have an equal sign, therefore it's just this and that. And then here it's the real number line R, negative infinity to infinity. So that is it. That is it with these things. So therefore, the next part, maybe you have to give examples, and then later on solve the exercise. But let me see the exercises. No, examples, I mean. Examples. We are to state whether it's closed and whether it's bounded. So state whether closed or bounded. Okay, the question says state the interval type. State the interval type and whether it's, how is whether written, I think this way, whether it's bounded or not bounded. Okay. A 1,10. This is, what is this? Okay, let me write many examples. B -3,0. C -5, -1. And then D -100, -99. E negative infinity, 2. F 0, infinity. Okay, I'm gonna write our answers in blue. This one, it's closed interval, and it is bounded by numbers, closed and bounded. This one, it's open because 3 is not included and 0 is not included, so it's an open interval. Open interval and bounded. Remember, those that are unbounded are those that have infinity and negative infinity, right? And this one, it's not conclusive. Interval type is not conclusive. Not conclusive, but bounded because it's bounded by numbers. And then this one here, it's closed and bounded. And this one here, it's not conclusive because 2 is included, right? Not conclusive. Not conclusive and unbounded. And then this one here, it's open and unbounded. Unbounded. Hey, and unbounded. I think this is clear because I think it's easy. And hey, let's see how it rolls. Let's move to the next subtopic. Let me see the post. Okay. Yeah. Okay. Moving to the next one. You're going to have absolute value or distance. Absolute value or distance. Absolute value or distance. Absolute value or distance. Remember that distance is always positive, or should I say displacement? Yes, distance or displacement is always positive. We are never going to have a negative distance. Or magnitude. When you go to vectors, we're going to talk about things like magnitudes and whatnot. And distance between 2 points, they are really absolute values because they're always positive. Even if you are moving in the negative direction, but we count that you moved a certain distance. So absolute values are never negative. So the definition of an absolute value, we say that if a certain number, definition, we say that if A is a real number, if A is a real number, if A is a real number, then the absolute value of A, the absolute value of A can either be that modulus of A is equivalent to A is a positive. That means that here A should be greater than 0 or equals to 0, greater than 0 equals to 0, or it can be negative A if A is strictly less than 0. So I think we need to talk about the modular signs. Remember that when you say absolute value of A, we mean that whatsoever number we have, we're going to have its positive. Okay, let me put some NB. Let's talk about what modulus does or what absolute values does. Okay, talk about modulus or absolute value. It's the same thing. That is, I mean these signs. This bars, we're going to put a number in the middle. So we say absolute value of or modulus of. So we're going to talk about what they do to a number. The modular signs leaves a positive number as it is, or leaves the positive number positive, and it negates negative numbers. Hence all resulting to positive values. All resulting to positive values. All resulting to positive values. Whatever, it doesn't matter. E.g., A, absolute value of 1 is equals to positive 1 each and every time. B, absolute value of negative 2 is equals to positive 2 each and every time. Absolute value of 0, it's equals to 0 because of this property, you see? Yes. And then, okay, it's supposed to be C. And then D, Okay, let me write it there. The absolute value of -9 will always be 9. Positive. E, absolute value of negative that, it's going to always be that number. What is that? 10,000. Yes, to always be that. That is how absolute values work. So now I have to include something, I think, upon properties of absolute values. Yes, yeah. So I guess it's easy here. I guess it's easy. There is no problem. So let's go ahead to properties. Okay, let me rewind. We say that if A is a real number, then the absolute value of A, it's represented as absolute or modulus of A is equivalent to A if A is 0 or positive, and it's negative A if A is less than 0. This simply implies that when, after having modulus of A, you can get positive results if A was already a positive number or 0, or you can get a positive result if A was a negative number, because what modulus does to A, they negate the number, so it becomes positive. I mean something like this. I mean, according to my definition, I mean, let me put a different color, this funny one. I mean, modulus of -2, modulus of -2, it's equals to, remember we said it negates negative numbers. It negates negative numbers. Remember by director numbers, we say a negative and negative, it's a positive. So then it becomes positive always. And modulus of 2, it leaves it as it is. So all their outcomes are always positive according to modulus. I guess you understand. So that is how easy really it is. So it is really not a big deal. So it means that these are the result of modulus of 2. Modulus of 2. So that is how easy it is. So I guess we can all see that. Or should I say plus or minus? Yes, plus or minus 2. Either way you want to put it. So that's it. So let's move on to the next one. We're going to talk about properties. Properties of modulus. What do they call them in your book? They call them absolute values. Let me call absolute values for uniformity. Properties of absolute values. Properties of absolute values. Absolute. Yo guys, I'm failing to write. I don't know where I'm rushing to. Properties of absolute values. So properties of absolute values. I'm just going to state out just a few, not a few anyway, all I have to say. So we have that number one, we have that absolute value of a number, it is always going to be positive no matter what, because of what I just said, that absolute values, they negate negative numbers and they leave positive numbers as they are. So that is how easy it is. And then property number two, absolute value of a negative number, it is going to be always the same as absolute value of a positive number. That is, a work into that, you can represent that as, we can say, yeah, let me see, is yellow good? No, it's not good. Let me see a different color. Okay, what should I pick? Let me just pick this dark green. Okay, let me take this back. Okay, we say that. Remember, we talked about the negatives. Remember, by the properties, we say that absolute value of A is equals to either A or negative A. That is, if A is greater or equals to 0, this is negative A if A is smaller than 0. So if this is the case, that simply implies that, I'm proving this by that. That simply implies that negative a under modulus is the same as negative. It is always the same as negative a, which is always going to be positive a, right? And on the other hand, modulus of a, by that which I said on the previous page, that modulus of a positive number, it is left as it is. So we just collect it as positive as it is. So then this is equivalent to that, which implies that this here is equivalent to that, which suffices our property. And then number 3, let me go back to my color for uniformity. Yeah, what color was it? I forgot. Okay. Anyway, good. Number 3. Okay. So we talk about multiplication. We say that modulus of A times B, modulus of their product is equivalent to the product of their moduluses, like each of them having their own modulus. So easy here, we can say modulus of 3 times 2, it should be the same as modulus of 3 times modulus of 2, which means this is going to be 6, modulus of 6, and then here we should have modulus of 3 is 3, and modulus of 2 is 2, and then here modulus of 6 is always going to be 6, and 3 times 2 is always 6. Sorry about that. It's always 6. I think we're good about that, are we? Yeah, I know we are. So that is how easy really it is. It will be 6 as well. Henceforth, the two are equal, which suffices, or which implies that our property is correct and we should not worry, yes, about it. And then number 4, we talk about the division of a fraction, but all of that being under a modulus. Modulus of A over B, it's equivalent to separation, that is modulus of A over modulus of B. And then we can do the same proof about that. So easy again for this. Easy. Modulus of negative 2 over 3 is equals to negative. I am sorry, I used the number that I don't know. Hey. Let me use a 4. Hey, I wanted something which can be converted to fractions. But anyway, it's negative. So if it's negative, we can simply, it's a negative number, so we can multiply it by a negative number. So that is, we can write it as negative of negative 2 over 3. Then that simply will be positive 2 over 3. And this again can be written, or with this left-hand side, we are going to have negative 2, modulus of negative 2 over modulus of 3. Modulus of negative 2 is going to be negative 2, negative 2 over 3, which is equals to 2 over 3, which is, this is equivalent to that, which simply implies that our property is correct. So these are our moduluses, and everything about it, it's easy. So just a walkthrough, I think. It's just a walkthrough. So our modulus is always, they're going to provide us with positive answers no matter what, 0 or positive answers. And modulus of a negative value, it is the same as modulus of that very same value but being positive, because of what I explained that side, that modulus negates negative numbers and leaves the positive numbers as they are. And here we say that modulus of a product of numbers, it is the same as the modulus of each single product, and at the end having them multiplied together. So they yield to the same positive number, and same for division. Modulus of a fraction is the same as modulus of the numerator over modulus of the denominator, hence, which was proved by this smaller example here. I guess we are all good. And then let's go to the next one. We're going to talk about certain property, that is the distance between 2 points on the real number line. The distance between 2 points on the real number line. So that is, let me change color to them. The distance between the distance between 2 points
2 points in R. Distance between 2 points in R. The distance between 2 points in R. For example, before really anything general, we can simply say if we have one number here, real number line, we have our number there, 2 and our number 5. What is the distance between 2 and 5? Obviously, we are going to count the units in between, and it's going to be 3, right? And what is our distance between 5 to 2? How many units really? It's going to be 3. But we will be counting going backwards, but still, because it's distance, we always say it's positive. And then by that property is being proved by, we say that the distance between point A and B, D of A comma B, this reminds me of real analysis. Okay, the distance between point A, this D is for distance, right? There's A and B. It's only because we are assuming, okay, let me write that condition. We are assuming that A and B are real numbers. So the distance between A and B is equals to modulus of B minus A, because by assumption, we assume that B is bigger than A. Yes, B minus A, and it should be the same as A minus B. And that distance should be the same. Proof for this, we can do some little working so we can show how it yields to that. We can say that, let's see if at all B minus A is equals to that. So if we have e.g. or further explained, if we have B minus A, so if at all the yield here, okay, let's suppose that this one is positive. Let's suppose that this one is positive. Remember that for our modulus, always the yield is positive. Yes, if B minus A is that. So then now, if A minus B is negative, if A minus B, if what is inside is negative, then this implies that we're going to simplify it and write it as negative of A minus B. In which, when you are going to simplify, you're going to get, skip this step, negative A plus B, which can be rewritten as B minus A, which is simply that. And we assumed that this is positive. So therefore, this is positive and this is positive according to our assumption. And their magnitude is the same. Therefore, the property is true. If you didn't get what I was saying here, just to get that the distance between 2 points is always going to be the same, no matter where you're starting, but the distance is always going to be the same. I think you got that. And then moving further, I think we just left with some examples. Okay, deal with properties and then examples. Okay, properties, basic rules of algebra. We have a bunch of properties. Basic rules of algebra. Let me deal with those. Basic algebra rules. I know we dealt with algebra in junior school, Form 1 or grade what? Grade 8, yes, whatever. Yes, so okay, in this during our explanations, we are going to assume, or we're going to hold the assumption that A and B, okay, A, B, and C are elements of real numbers. We're going to hold that, or we're going to assume that they are real numbers. So we are going to have properties like, how many of these? There are many. I don't want to go to Roman figures because they will confuse me on the way. So property number 1, we can talk about commutativity under addition. Commutativity under addition. Commutative, this is a V, sorry. Commutative property in addition. Commutative property in addition. Commutative property in addition. It doesn't matter how many times we have, 3 or 4, whatever, but what the commutative property says is that the position of your term or your number or your variable doesn't really matter. If at all it's positive, it doesn't really matter. Or if it's negative and it goes with its sign, it does not matter. Position doesn't matter. So we say that A plus B is equals to B plus A. So they are always going to be the same. And okay, I don't know if I should include this, but negative A plus B is always going to be B plus negative A, which is equals to B minus A. If it's confusing, let's ignore this one, this last line. So yeah, this is just it. And then e.g. example, we look at, look at example, let's say there, okay, so we'll be there. Yeah, you say 2 plus 3 is what? It's 5, right? And this is as well equals to 3 plus 2. So the property holds, and that is correct. So that is what the commutative property says. And then property number 2, it's saying commutativity. To read that. Commutative property in multiplication. In multiplication, we say that A times B is equals to B times A. It doesn't matter which one comes first, as long as we took them with their own signs, we're good. Then e.g., so that one is an example where we have, okay, maybe it doesn't. Okay, example, e.g., 5 times 2, it's a 10, which is as well equals to 2 times 5. So this is the property of commutativity. I guess it's clear. So the next one, we're done with commutativity. We talk about associativity. Associative property, I should have said associative. Associative property. Property in addition. In addition, this one talks about the brackets. It says that if we are to solve first a certain thing under addition, they're the same as, okay, suppose we have 3 numbers, A plus B plus C, C being outside the bracket. It says that these things are equivalent to A plus B plus C, but the last 2 being in brackets. So I guess it's clear, e.g., change color. Okay, e.g., 2 plus 3 plus 1 should be equals to 2 plus 3 plus 1. The last one's being in brackets. So here, simplifying that, we're going to get a 5 plus 1 is equals to, here it's going to be 2 plus a 4. And this is a 6, and this is a 6. Therefore, our property is true. I guess that is easy. And moving to the next one, we have associative property under multiplication. So it's, I don't know if I was numbering with letters or with numbers. So this is number D. Yeah, number D. Associative property. Associative property in multiplication. Multiplication. So still no further explanation. You just need to know about multiplication. See that? If we have A times B times C, having multiplying the first factors, it is the same as you can multiply the last numbers. like that. It's the same, easy. Okay, change columns will be there. Sorry about that. So if we have 2 times 3 times 4 is the same as 2 times 3 times 4. The last one's being in brackets because this will be 6 times 4, it will be a 24. And then here we're going to have a 12 here times 2, it's still a 24. Then that is correct. I think we can see that. And then the other property number E, is the distributive property. Distributive property. Distributive property is simply under expansion. Simply under expansion, we say that if we have A bracket B plus C, we can remove brackets by expanding and having A times B, and then we're going to have AB plus this plus sign, right? A times C, which is going to be AC. So very easy. E.g., I think there's no need for me to give an example, but let me write an example. Easy, if you have 1 times, not 1, let me use 7 times 1 plus 2 should be equals to 7 times 1 plus 7 times 2. This is 7, this is 14, so it's going to be 21. Everything is going to be 21. Or we can simply solve what is in brackets first. We're going to get 3 times 7 is 21. So all of them are 21. Therefore, this property tends to be true because the left-hand side is equal to the right-hand side. I think we're good. And then we go to another special properties with properties which contain inverses. Inverses implying or leading to identities. So that really is easy. So additive identity property, I'm gonna number them. I'm gonna write our notes in red. Additive identity. Let me see a better color that I can choose. Okay. Nothing, I took that. Yeah. Okay, so additive property and the addition. Additive identity, sorry. Additive identity in addition. We say that. What is the additive identity? Additive identity is 0. Additive identity is 0. So you're going to prove that by saying that additive identity in addition is 0. So we're going to see that a number A plus 0, it is not going to change the identity of that number. Therefore, we say 0 is an additive identity because if you add 0 to a number, that number doesn't change. Its identity still remains. Okay, maybe e.g. 2 plus 0, 2 plus 0, still it's 2. 2 remains 2, so its identity still it holds or is there. But in figure 2 can have multiplicative identity in multiplication. Hi, what is it? What did I say? Additive identity, obviously. Additive identity, obviously, guys, I did not, it wasn't important for me to write this. It's not necessary. Because when I say additive, I mean addition. Ne? So the next one is going to be multiplicative identity. I want to call it ID. Don't write ID, please, in your test exam or whatever, or your notes, your revision notes. So that one is obviously 1, because when you multiply a number by the multiplicative identity 1, it doesn't change. E.g., 3 times 1. 3 times 1 simply is 3. That 3 did not change its identity. So we say that 3 is multiplicative identity. I think it's easy. The next one, we are going to talk about additive inverse. Additive inverse. Additive inverse. Additive inverse. we say that when you add a number to its identity, you are always going to get an additive, oh, sorry about that, I made a mistake. When you add a number to its inverse, you get an additive identity. You get an additive identity, which is always going to be 0. And we can simply have an example. Okay, I should say e.g., not this arrow. 3 plus negative 3. Remember that the sign of positive and negative, they give you a negative. So 3 minus 3 is 0, which is an additive identity. And multiplicative identity, inverse, sorry, multiplicative inverse. Oh my God, I'm failing to write. Jesus Christ, help me. Multiplicative inverse. My letters are sloping. Multiplicative inverse, we're going to say that. Remember, the numbers multiplicative inverse, it's a reciprocal. I hope you remember reciprocals from fractions. So a times 1 over a is equivalent to multiplicative identity. So here we say that from number 1 there, we say that negative a is an additive. It's an additive inverse. It's an additive inverse of a. Negative a is an additive inverse of a, because when you add them, they give you 1. And from here, we say that 1 over a is multiplicative. Is multiplicative inverse of a, because if you multiply them, they give you 1. So I guess that's clear. And then we can have, oh, we end there. So we can give examples with numbers and it's going to be the same. So yeah, all these other properties, they're easy, they're always there. So I think we should stop here and then do examples So let me see. Okay, let me do this first. So we're going to have properties. We have, let me see. We know them from junior school. That is properties of negation and equality. Sorry, properties of negation and equality. Those ones I'm pretty sure we know them from junior and senior school. And then the next one is properties of 0. Properties of 0. I know we know them. Properties of 0, or should I say 0 properties? Let me change the color of our notes. 0 properties. 0 properties. I'm not going to talk much about them, but I'm just going to list them. So the first one, we have that. Okay, I should have used Roman figure because I'm going to use A in my denotions, you know. Okay, Roman figure 1, we say that A plus its additive identity, which is 0. A plus its additive identity, which is 0. And it's always going to be A. Roman figure 2, A minus its additive identity, or we can say subtractive identity. Still it's going to be A because it doesn't change its identity. Either you add it or you remove it. And yeah, and then we can have those of division, number 2, number 3, I mean, we have that 0 over a number. It is always going to be 0 because you can't divide 0 by this many times number, but you can only divide it 0 times because you can't even divide it once. So then the next one is A over 0. It's going to be undefined. Is undefined. It's undefined, which implies that we don't know the solution. The solution is not defined. And then we have the 0 factor, the major one. This one I love it. because we're going to use it until higher maths, you know, as we move on, we're going to use it. So it's the zero factor. Number 5. No, 5 is written as V, I think is in Roman figures. Is the zero factor property. The zero factor, it needs a different color, fellows. It needs a different color, fellows. Let me honor it with a different color. Should I honor it with a white color? The zero factor property, the zero factor property, the zero factor property. It says that if you have two numbers or two expressions, A times B being 0, that simply implies that either A is a 0 or B is a 0. This we are going to use to solve quadratics. So that is how easy it is. So please don't forget its name, zero factor property. So I love it because it's very useful and we're going to use it. Okay. So we're going to have properties and operations of fractions. We know fractions, operations of fractions, operations on fractions, operations on fractions. Operations on fractions. We know that you can have number 1. I'm not going to state the property. Okay, I'm just going to call it out. I'm not to write. It's the equivalent fractions. Equivalent fractions. You know the thing that you always talk of when you say we cross multiply. It is what you're going to do here. But cross multiplying, remember, it's not mathematical. It's just a shortcut. So this is only true if and only if AD is equals to BC. If and only if, remember, it's only true if and only if. And then the next one, the rule of signs. So, you know, negative A over, or I bound them or I put them together. Okay, negative A over B is the same as negative A over B, and it is the same as A over negative B. So they are really the same. And negative A over negative B is the same as A over B, because those negations, they negated each other and they tend to be a positive. Remember that when you divide a negative by a negative, you get a positive number. Then Roman 3 is addition and subtraction. That is, if you have two fractions, A over B plus or minus C over D, what you have to do first, remember, is to find their lowest common multiple. Then these ones they don't have because they are just numbers. If it's numbers, you have to check their lowest common multiple, because if you do so, you won't have to simplify at the end of your answer. But if you don't have, if it's numbers, if it's fractions, if it's expressions, or if it's variables, you simply multiply them and do your math. So we are simply going to say B into BD is going to be D, and then D times A is going to be AD. Then take the sign, whatever sign we gave, and so here they are all, I'm going to put them all there. If it's minus, we take minus. If it's plus, we take plus. Okay? And then we're going to say D into BD is B, then B times C is going to be BC. This will be your product. This will be your yield or your result. And then at the end, you will have to simplify them if at all you could. So, and then multiplication, these things we know. A over B times C over D. You straight multiply numerator with numerator and denominator with denominator. So you're going to get AC over BD. So easy. Division. Then division is number V. Division, that is A over B divided by C over D. Remember what we said about division? We said you multiply by the reciprocal of the last fraction. You multiply the first fraction with the reciprocal of the last fraction, which really we can say you flip the last fraction and multiply. That is going to be A over B times D over C. And your answer will be AD over BC. I guess we're good. And then here, suppose looking at those, we say that C should never be 0. In fact, all numbers which are beneath, all numbers which are under the denominators should never be 0. So this is C, and then that could be D, and then that could be B. B and C should never be zeros. So by the rule. So I guess we're good. And then that is where we're going to end the property things and talking about whatever. So the next one is going to be on examples. So thank you very much. This is it for the first video. God bless you all. And hey, let's continue believing in him, for he shall surely give us rest. So I'm failing to, my God, let me move this first. So you do that. Yeah, okay.